Okay, so we're gonna have a lecture on solving the Poisson equation by using the fundamental solution to the Laplace equation. So now let me recall um, some basic facts about the fundamental solution, and then we go from there. What I wrote down here was that we already derived what is the fundamental solution. In 2D, we have that is minus 1 over 2 pi natural log of the length of x. And then in 3D or height, we have that the fundamental solution is a constant 1 over n times n minus 2 times alpha n times the length of x to the power 2 minus n. This function is defined everywhere except the origin. Here, let me recall that alpha n is nothing but is the volume of the unit ball in Rn. Okay, so this is the volume of the unit ball in Rn. We will discuss a bit more on this matter soon. Okay, so again, the point here I want to recall is that our fundamental solution is smooth everywhere except the origin. And in fact, you can see that as x tends to 0, it's blowing up either in the logarithmic way or in the polynomial way, depending on the dimension. So here I drew a sort of a schematic picture of phi. So this is in the case of 3D or higher. You see that, it sort of decay polynomially at infinity and then blowing up also, polynomially at 0. And phi, the fundamental solution, solves the Laplace equation everywhere except the origin. Okay, so we have this. Okay. Our lecture today is about how do we use this fundamental solution as a building block. It's a building block to solve the Poisson equation. The Poisson equation is of this form that minus Laplacian of u equals to f of x in Rn. Okay, so I put some, let me write out the assumption for f. So here I would say that here f of x is a given source term that is given to us on Rn. And as we, intuitively, our given source term can be something like this, and then we try to sort of like break it into pieces and, use the fundamental solution as building block to put things together to solve the Poisson equation. Let me put the assumption on F. Let me write down and then I'll explain to you the terminology. We assume that F is in C2, okay, C2, C, little c here represents for compactly supported in Rn. Okay, let me write out where the space of C2, CRN is the space of all function, let's say H, mapping from Rn to R, such that H is in C2 of Rn, and H is compactly supported, that is, H is 0 outside of a big ball, okay? And H is compactly supported. That is, there is radius r greater than 0 large enough so that h of x is equal to 0 for all x greater equals to r. Okay. So in this picture up here, for example, here f, you can see that, in this schematic picture, f can be not 0 inside this region, which is sort of represents for a ball of center 0 radius r, and f is totally outside outside of the ball. Okay? So that's sort of the thing, the assumption that essentially we assume that f is only non-zero in a ball, right? And then 0 elsewhere. Okay. So let me state right away the theorem, and then we will proceed to prove it today in this lecture. Theorem, there's only one theorem for this. It's basically solution to the Poisson equation 1. Okay. So we set u of x as, again, we're gonna use phi as a building block. We're gonna put things together in this case that we are sort of integrating phi with f in a convolutive way. But I mean, let's say that we don't even need to know about that. U of x equal to the integral in Rn of phi of x minus y fy dy. Okay, so I'm integrating the fundamental solution with the source term f in this manner. And you can see that by a simple change of variable, this is equals to integral in Rn. I'm just switching the row of x minus y and y, right? I'm noting that x minus y plus y is x, By switching the row, I can see that, well, by a simple change of variable, this equals to phi of y f of x minus y dy. Okay, so let u to be this formula. And as you notice, integration is nothing but summation. So we should think about like we are taking summation of a bunch of fundamental solutions with the weight f. Okay, so set u to be this formula. Then the theorem says that then we have the first thing is that u is a function in C2 of Rn. So u is twice differentiable and its first and second derivatives are continuous. And the second point, the second claim is that u solves the Poisson equation. So it's 1. That is minus Laplacian of u of x equals to f of x in Rn. Okay. So clearly you can see that either I'm integrating it this way, or by, the first way, or by a change of variable is the second way. That essentially, again, I'm using the fundamental solution at building block. I'm putting it everywhere. And in each of the place, I'm multiplying it, if I put phi of y, I'm multiplying it with f of x minus y, and I'm putting things together to have that is a solution to the Poisson equation. So that's the theorem. We're gonna prove it. Okay. But before proving that, maybe we need to do some preparations, quick preparations. So let's say some basic facts in order to prepare to prove our result. The first thing is exactly, we need to address about that sort of compactly supported function, right? So we are given that f is in C2C of Rn. Okay, let's write out explicitly one more, which means that there exists a radius r greater than 0 such that f of x is totally 0 for x greater equals to r, right? Okay, so maybe let me draw or here. This is 0, the radius r. We have f is totally 0 outside here. So what matters is only that, the value of f in here matters, right? I mean, outside the ball, there's nothing. Okay. So f is, matters only inside the ball. So clearly from here, we do have that this implies that fxi x equal to 0 for x greater equals to r. And also like if you differentiate in any directions, fxi xj x also equals to 0 for x greater than equals to r. For any 1 less than equals to I less than equal to j. Yeah. So you differentiate, outside is always 0. Okay. So that means that we have f fxi xj or compactly supported in the ball center 0 radius r. Okay, here compactly supported meaning that, the place where f is not 0, right? Again, f is 0 outside, or fxi is not 0. fxi xj is not 0. Those set are contained in this ball. Okay? And moreover, we are given the fact that they are continuous functions. You have learned from analysis is a continuous function, has max and minimum value in a compact set, right? So again, it's 0 outside of this ball, and in the closed ball center 0 radius r, it's a compact set. So hence we do have that maximum of x in Rn, f of x, which is just equals to maximum of x in this sorry, not unit, closed ball center 0 radius r fx exists, and the same holds true for fxi or fxi xj. So max of x in Rn, fxi of x equals to max of x in this compact set, and same for okay. So for simplicity, let me define this sort of constant. So I'm gonna set a constant k equals to max of x in Rn of f of x. I'm just gonna sum up all the maximum value, the summation I from 1 to n, max x in Rn, fxi x, the summation ij from 1 to n, max x in Rn of fxi xj of x. Okay, I denote k to be this constant. This is a finite constant. Okay, and okay, let me put a highlight here. So define this constant k to be like this, which is a finite constant, and we have simply that fx or fxi x or fxi xj x is always less than equals to k for all x. Okay, so we essentially define a bound k, which is going to be an upper bound for all the value of f or its first and second derivative. Okay, that's the constant k we define. So that's the first fact. It takes a bit of time, but okay, whatever. Here's the second fact. It's about an integral identity. This is about, how do we integrate a function in a ball, right? Let's say that we are in a ball of center rate 0 radius. Let's call it a different number, radius little r, okay? So how do we, I mean, of course, we know how, so for phi being a continuous function in this ball, center radius 0 radius r, how do we compute this integral b0r of phi x dx? Okay. Again, this is just a Riemann integral, and one way to think about this identity is that you can think about the ball of center rate 0 radius r is essentially a union of spheres of radii sort of ranging from 0 to r, right? So there's an identity that simply I have b0r is the union from 0 less than equals to s less than equals to r of the sphere of center 0 radius s. Okay, so this is the identity. So here let me say the sphere of center 0 radius s is simply all points x in Rn, so that the length of x equals to s. Okay, so this is the sphere of center 0 radius. And so you can think about it as kind of like a ball. We can peel it into layers and layers and layers of spheres. Okay, so or you can just pack all the sphere to have a ball. So this integral identity is simply telling us that, when we integrating it in this ball, we can simply doing it so that we integrate it in each of the sphere and then integrating in the radii. So integrating in the radii from 0 to r, and then integrating in each of the sphere, we x ds. So I'm integrating first with the surface with respect to the sphere, okay? And then I'm adding everything up, right? Adding every spheres up. So then I'm integrating it with respect to the radii. So I have this important integral identity that we also need to use in order to prove this important theorem. Now, this simple integral identity gives us something interesting. I want to address that as an application first before we go to the main proof. So an application. This integral identity is that we can relate the volume of the unit ball. I mean, remember that we defined earlier the volume of the unit ball is alpha n, right? Which is again the volume of this unit ball to the surface area of the unit ball. Okay. Of the unit sphere. Surface area of the unit sphere. This is the unit sphere. The surface area can be written like this. Between the absolute value is the surface area. Okay. How do we relate this? So let me recall simply that. So note. Okay. Let's note it first and then we plug in, right? So how do I measure the volume of the ball of center 0 radius r, right? Um, again, this is just dilate from the radius 1 to the radius r, right? So this is simply just r to the n times the volume of the unit ball, right? Because the volume, the unit is of the volume is unit to the power n, right? And this is r to the n times alpha n. For the sphere, if I compute what is the surface area of the sphere of center 0 radius r, then the surface area, the unit length, the unit is r, the length to the power n minus 1, right? So r to the n minus 1 times the surface area of the unit sphere. Okay, so those are the two things. All right, now let's apply this integral identity. How do we apply it? Well, we just let phi equals to exactly just 1 in the integral identity. Okay, and and we can also let r equals to 1 there, right? In exactly just that integral identity. Okay, then the integral identity tells us that if we integrate in the unit ball 1 dx, this equals to integral among all the sphere of radii from ranging from 0 to 1 on edge of the sphere, 1 ds. ds is the surface area and d little s just the radii. Okay, the left hand side is nothing but exactly just the volume, right? This is alpha n, which is the volume of the unit ball. Okay, the second object, I'm using the above identity we just discussed here. Edge of the sphere of radius s has the surface area of s to the n minus 1 surface area. Yes. Okay. And this surface area, the unit sphere, is just a constant. I pull it out. S to the n minus 1 ds. And this is an elementary integral, right? This is 1 over n. You can check it. So this gives us an important identity. That the volume of the unit ball equals to 1 over n times the surface area of the unit ball. Okay, we are not talking about unit here. We omit all the units. Or equivalently, the surface area of the unit ball, unit sphere, is equal to n times alpha n. It's a very important identity. All right. Okay. With a lot of preparations, we are now ready to come back to the main theorem here, that we are solving the Poisson equation, right? But I have spent quite some time to tell you about 2 or 3 basic facts. Okay, let's come back to prove the theorem. Let me recall the formula so that you're not forget. So proof of the theorem. Okay. Let's recall the formula of u, right? So ux equals to integral in Rn phi of x minus y fy dy, or by change of variable symmetry, you can think about it that way, phi of y f of x minus y dy. Okay. So depending on situation, we can use different formulation, right? Now let's first prove that u is twice is C2, right? So the first claim we need to prove is that we need to show u is in C2 of Rn. All right, so when I need to show that u is C2 of Rn, that means that I need to differentiate twice, right? I looked into the one of the two formula. You can see that the first formula, x is in the phi. Remember that we already said from the beginning that phi is, blowing up at zero, right? So it's a little bit bad at zero. I would try not to touch phi there. I'm now using the second formula. Why is the second formula better? Because you can see that x appears here, right? Yes, in f. And f, we are given that f is C2, which is nice, right? So naturally, I'm just using the second formula and I'm differentiating it. So let's do it. I have u of xi of x is equal to del over del xi, partial derivative of the integral in Rn of phi of y, x minus y dy. And again, we know that f is nice. We can put the derivative inside the integral. So this equals to integral in Rn phi of y f of xi x minus y dy. Okay, nice, right? And similarly, if I differentiate twice, uxi xj of x is equals to del over del xj of this integral. And again, I can put the integral inside the the partial derivative inside the integral to get. Okay, both of these are nice and well defined. Remember that f is a given C2 function. Okay, so this allows us to see that uxi xj continuous function for all indices I and j between 1 and n. Okay, this gives us that u is a C2 function, right? Because the definition of C2 function is that the functions first and second order derivatives are continuous. Again, we only actually need to check that the second order derivatives are continuous. Okay, so that's that. Now, the second point, which is actually the main point, right? That let's put it out. That finally, this is not easy, but we need to show that, u is now C2, right? We can differentiate twice. Minus Laplacian of u of x equals to f of x in Rn. That's what we needed to show. Remember that we already computed the second order derivative or partial derivatives of u up here, right? Now we just, put it together to have the Laplacian first to see what's going on. So by the above computation, we have minus Laplacian of u x. Again, by definition, minus Laplacian is minus summation of all the repeated second order derivatives, xi of x. And by using this above formula, I just highlighted, this is minus summation I from 1 to n, integral in Rn, phi of y, f xi, not xj, xi of x minus y dy. Okay. And this repeated sum is exactly the Laplacian, right? So this is minus integral in Rn, phi y, Laplacian in x of f x minus y dy. Okay, so I have this formula. Right, that's what we have. There's a note here that I want to say. So note that, the Laplacian in x of fx minus y is equal to the Laplacian in y of fx minus y, right? So let me write that. Laplacian in x of f x minus y equals to Laplacian in y of f x minus y, because if you differentiate once, there's a minus sign x minus y. Okay, let me write that. Del over del y, I of f x minus y would equals to minus 1 times times del over del x I of fx minus y, right? Because of the minus size, but if you differentiate it twice, del square over del y I square fx minus y, it would just, minus 1 square, right? Del square over del x I square fx minus y, which is exactly del square over del xi square fx minus y. So that gives us that Laplacian in x of fx minus y is equal to Laplacian in y of fx minus y. Again, we have computed that the Laplacian of u equal to this, right? However, this is not enough to get that, we need to show that this thing equals to f of x, which is not enough. We have not used the fact that, so we need to use the fact that Laplacian of phi of y equal to 0 or minus Laplace in Rn takes away 0. Okay, so we need to use this fact. We have not used this property of the fundamental solution. So how do we use this fact? Well, we need to integrate by part twice to take the derivative from Laplacian of f to Laplacian of phi, right? Okay, so anyway, let's write that slowly. So hence by this point that we have minus Laplacian of u on x equals to minus integral in Rn phi of y Laplacian in y fx minus y dy. Okay, now this is normal. So the point now is sort of to integrate by part twice to kick Laplacian in y of f to Laplacian in y of phi, right? Because we take two of the derivatives from f to phi to get that. Remember that f is totally nice. F is compactly supported. It's 0 outside of a compact set. Everything is nice, but phi is not nice, right? So let me write that. So f is very nice, and f is 0 outside of of the ball. B0R. Okay, so it's 0 outside, but phi has a singularity, or phi blows up at 0. Okay, so phi is not nice at 0, it's singular at 0. So how do we do integration by part twice to take the derivatives from f to phi? Well, so what we need to do is that we need to essentially how to say it, we need to sort of like cut out the singularity, right? Singularity. In this case, there's only one. So, the idea is simple. Let's draw a schematic picture. Phi blows up at 0 here, okay? So the idea is then, not dealing with the whole domain, but instead we sort of like single out the singularity. We put a small ball around it. So, put a ball center 0, radius epsilon around it. And then we cut it out, right? We cut out this little ball that has a singularity. Okay. And we deal with the outside part. So we deal with the outside part. Okay. All right, so that's the idea. Let's write it down. Okay, so let me record minus Laplacian of u. We have computed this is integral in Rn. Phi of y, Laplacian in y of fx minus y dy. We put it into two pieces. The first piece is the one that has the singularity. So this is a small ball that we circle around the singularity. Okay, and the second part is that we remove the singularity, right? Remove the blowing up part. Okay, so we put it into two pieces. Let me name the first one to be I of epsilon, second one to be J of epsilon. We divide and concur, right? We divide it in two pieces. The first one contains a singularity. The second one doesn't have anything, any singularity, right? Phi is nice outside of this small ball. Okay. So the point now is that, let's say that the first claim here, claim is that I epsilon is small and limit as epsilon goes to 0 of I epsilon equal to 0, meaning that although that it contains a singularity, but it's going to 0. Okay, so that's a key point. How do we do this? Let's prove this first claim. Prove. Okay, let's put the absolute value around I epsilon. This is less than equals to integral of this inside this unit ball phi of y, Laplacian in y of fx minus y dy. Okay, I can put the absolute value inside. This is less than equals to. Remember that phi is always put absolute value around phi. That's fine. Phi of y times Laplacian in y of fx minus y dy. Okay, now let's recall the first fact that we have said about phi, about f. The first fact we said about f is that f is nice, fxi, fxij, they're all nice and bounded by k, this constant k that I highlighted here, right? So I'm using that fact to bound the Laplacian of f. So recall that we have, let's say that f of xi, x minus y equals to f of yi of x minus y. This is bounded by k, right? And the Laplacian is just summation over all I. This implies that Laplacian in y of x minus y. That's equals to summation I from 1 to n. That's equals to n times k, just a constant, right? I mean, so this implies that I epsilon less than equals to a constant n times k times this integral. And phi is our fundamental solution. It has explicit formula, right? So let me say the right away that this is less than equals to some constant. Yeah, let's say that this is less than equals to some constant times epsilon for n greater equals to 3 and a constant times epsilon square log of epsilon for n equals to 2, where c greater than 0 is a large enough constant. Okay, so if we can prove this, then you can see that clearly this implies the limit as epsilon goes to 0 by epsilon equal to 0. Okay. Let me only check the claim for n greater equals to 3 because for 2 is the same. Okay, so check this for n greater equals to 3. Okay, so let's rewrite it. I epsilon is less than or equal to n times k times b0 epsilon. Phi of y, we have an explicit formula, right? So just write down 1 over n times n minus 2 times alpha n. X to the 2 minus n dx. Okay, the constant I just pull it out. So this is k over n minus 2 times alpha n. This integral. All right. Now this integral, I'm using the second fact that I stated earlier for you, that we can compute this integral by peeling the ball into various spheres, right? So this equals to k over n minus 2 times alpha n. The ball radius epsilon is turned into layers of spheres of radii from 0 to epsilon. For each of the sphere, x to the 2 minus n ds, d little s, okay? This equals to k over n minus 2 times alpha n, integral from epsilon 0 to epsilon. In each of the sphere, here, x to the 2 minus n, x is a constant, x is just s, right? So let's write it down. This is just on this sphere. X is just a constant, s to the 2 minus n ds, d little s. Okay, so this equals to what? It's a constant, so s to the 2 minus n times the surface area of the sphere, right? We have said about this. The surface area of the sphere is s to the power n minus 1 times the surface area of the unit sphere. Okay, so this cancel out and becoming what? Becoming s times the surface area of the unit sphere. Very conveniently and beautifully, right? Yeah, I think I made a typo here. This is epsilon square. Okay, so at the end of the day, we get this is k times the surface area of the unit sphere, n minus 2 times alpha n, integral from 0 to epsilon s ds, and this is exactly epsilon square over 2. Okay, so there's a constant. This is what I meant by there's a constant here. N minus 2 alpha n times epsilon square over 2. Okay, so we are done with getting rid of this term I epsilon. What we just show is that this term I epsilon, even though it's there, but it's vanishing. Okay, so we can now forget about it. Now let's handle the second term, which is the j epsilon. J epsilon is the term that we have cut out the singularity. Okay, and when we have cut out the singularity, then we can now do integration by parts. I think I have to do it a little bit quickly now. Let me write down. I have j epsilon is integral in Rn, takes away the small ball, Vy Laplacian in y of f x minus y dy. Okay, again we are taking the whole domain and we are deleting out just a small ball. Deleting out this small ball. Okay. How do we do integration by parts here? You know, don't draw the second picture. Zooming in a little bit. So this is a unit, not unit, I kept saying unit, the board radius epsilon. Integration by parts going to give us the baud rate term, right? There's a normal, unit normal vector coming in here, n, which is the unit normal. This is our domain, Rn takes away B0 epsilon. Okay, so when we do integration by part, this equals to integral in Rn B0 epsilon. I hit one of the derivative from here to here, so I would get d phi y dot with dy of fx minus y dy. I should have the minus size, right? Because I do integration by part. And then I have the baud rate term. The baud rate term is integral on this boundary, right? This boundary term of, you know, dy fx minus y dot with the normal vector and phi y ds. Okay, that's our boundary term, right? So in a similar way, let me call this one equals to k epsilon plus l epsilon. K epsilon is this first term, and L epsilon is a second term. In a similar way, like what we just did before, you can see actually even easier that L epsilon is also vanishing. It's similar because dy of f is bounded. Okay. Yeah, actually, yeah, I can actually prove that quickly. So in a similar way to the above, we do have that L epsilon is bounded by a constant times epsilon for n greater equals to 3 and a constant times epsilon log of epsilon for n equals to 2. Let me give a quick proof for n greater equals to 3. Okay, so L epsilon less than equals to integral on this boundary of dy of f x minus y. The normal have vector have length 1, so we can just throw it away. Phi of y ds. We have shown that, you know, f is bounded, right? So dy is bounded by same thing like n times k. Integral on this unit ball, sorry, I can say unit ball. Integral on this sphere of radius epsilon. Phi of y there is a constant. 1 over n times n minus 2 times alpha n. X to the power n minus 2, but x is epsilon, right? Epsilon to the power 2 minus n ds. Okay, so you can see it's the same thing. This equals to k over n minus 2 times alpha n, epsilon to the power 2 minus n times the surface area of this sphere, right? Which is epsilon to the power n minus 1, surface area of the unit sphere. So this is exactly that. So this is k times surface area of the unit sphere, n minus 2 alpha n times epsilon. So clearly this goes to 0 as epsilon goes to 0. Okay, so we can get rid of this L epsilon term, right? So we have many error terms, but all of them vanish as epsilon goes to 0. So what remains is this k epsilon term, the yellow highlighted term. Okay, so k epsilon equals integral in this Rn takes away the small ball, d phi y dot with dy of f x minus y dy. Now I'm hitting again one of the derivative of dy of f to d phi. So integration by part once more. Wait, I think I have the minus signs. Yes. So integration by part once more. I have this is integral in Rn b0 epsilon. Hitting all the derivatives from f to y now. So Laplacian of phi of y, f of x minus y dy, which is great. Again, remember that this is the domain that we have already deleted a ball. We really deleted a ball here. So outside in this set, this is 0. So this whole integral is 0. Because again, this is where y is not 0. But we are not done, right? There's a boundary term, as always when you do integration by parts. So what is the boundary term? There's a minus, so it should be minus here, minus the boundary term that I have d phi of y dot with the normal vector n f of x minus y dy, right? Let me draw another picture here. This is making the ball looking bigger, still radius epsilon, but I'm making it bigger so that it looks easier. This is a normal vector because we need to do the outward normal to this set, right? The set is this set. So the outward normal is pointing this way. Okay. So what really remains is only this integral. Okay, so we have k epsilon equals to this integral because the first one is 0. We are essentially nearly done now because now what we need to do is only to compute this integral. What is this? Well, let's just compute, let's just, wait, what am I, let's just compute for the case n greater equals to 3 as the case n equals to 2 is similar. Yeah, it just take too much time to compute. Let's write down everything, right? I have phi of y. We have computed this in class, but let's compute it again. 1 over n times n minus 2 alpha n at y. Y to the power 2 minus n, right? So if you differentiate phi, you would have, again, we have computed this in class. You can double check earlier, but if not, you can just compute it, right? You differentiate here, you have 2 minus n popping out. So it cancels out with n minus 2. You have minus 1 over n times alpha n, y to the power minus n times y. Or you can write n alpha n, y over y to the n. Okay, so that's the phi. Let me highlight it. Okay, and also what is our normal vector n, right? You can see that it's a unit ball. It's a ball radius epsilon. The normal vector is pointing out and pointing out of the of the domain outside, right? So it's pointing in this case. So the normal vector n is nothing but exactly minus y over y. Beautifully. Again, because let me maybe expand this a bit more. This is 0. This is the direction y, right? So the normal vector is going in the reverse direction of y. That's why I have the minus size. And I have to normalize it so that it has length 1. Okay, so then I can compute d phi y dot with n. Turns out to be exactly this, right? So minus 1 over n alpha n, y over y to the power n, dot with minus y to the over y. Minus and minus cancel out. So at the end of the day, I would have this is 1 over n times alpha n times 1 over y to the power n minus 1. Okay. Now we get back, we have k epsilon equals, okay, I have the minus sign still there. Wait, what? Give me 1 second. Let's go back here. Okay, yeah, I say one thing wrong here. No, not wrong. I mean, I forgot to put the minus sign here. So let me put this as just Laplacian of u. Okay. All right. So I would have k epsilon is equals to minus, right? Minus is this minus size. Integral on this sphere. dphi dot n is now explicitly computed to be 1 over n alpha n times 1 over, maybe let's write y to the n minus 1 f of x minus y dy. Okay. Yeah. Okay. No, not dy. Here I put it wrong. It shouldn't be dy. It's ds. It's the surface area, right? Because we are integrating it on the surface. Yeah, whenever we are on the surface, we need to put ds. So this is ds. And remember that on this sphere, 1 over y to the power n minus 1 is exactly 1 over epsilon to the power n minus 1. Okay. So this implies that k epsilon equals to minus integral on this units. Sphere of radius epsilon, 1 over n times alpha n times epsilon to the power n minus 1 f of x minus y ds. Okay. So remember, we have computed an important identity that the surface area of this sphere is nothing but exactly n times alpha n times epsilon to the power n minus 1. So this quantity is exactly the surface area, this one. Okay. Then this becomes exactly some sort of mean value theorem, right? Because we are integrating on a set of which that the surface area of the set is exactly this, right? So by the mean value theorem, there exists some y in y epsilon in this in this sphere of radius epsilon, that is the length of y epsilon is just epsilon, so that k epsilon is equals to minus of exactly f of x minus y epsilon, right? Because it's just an averaging, okay? And you can see that y epsilon is very small, it's just epsilon. So this implies that limit epsilon goes to 0, k epsilon turns out to be exactly minus f of x, okay? So let me recall here with so many things putting together. Laplacian of u is I epsilon plus J epsilon. I epsilon is negligible, so this is sort of going to 0. Okay. J epsilon is broken into K epsilon plus L epsilon. L epsilon is negligible, it's going to 0. Okay, so only K epsilon left. K epsilon is computed to be exactly this quantity into this red box. And then we just show that K epsilon equals to this one with limit is minus f of x. So thus, eventually, this is a very long proof, we get that Laplacian of ux equals to minus f of x, or minus Laplacian of u equals to f of x. We are done, okay? So that is for today's lecture. I will perhaps recall some of the important facts in the next lecture and discuss more with you. Thank you.